I'm Yi. I'm from University of Washington. Today I'm going to talk about our work on a general framework for information extraction using dynamic span graphs. So this is the joint work with Dave, Luan, Amy, Mary, and Hannah. So the task of information extraction is to map raw text to structured data formats such as database and knowledge graph. So information extraction can be applied to many different domains such as scientific papers, newspapers, and websites. There are many subtasks under the big umbrella of information extraction. For example, we need to extract entities. Say, for example, here, given this piece of raw text, we need to extract that Tom is a person, car is a vehicle, Starbucks is a location, and so on. And on top of those entities, we need to extract the relations between them. Say, for example, we need to extract that Tom is physically located at Starbucks, Tom and Mike are personally associated with each other. And then among all of those entities, some of them are actually referring to the same thing. So we need to do Coreference resolution to group the mentions that are referring to the same stuff to the same group. So the goal of this work is that we want to develop a unified system that can be applied to different domains and tasks. However, developing such a general system is not easy because, first of all, there is a challenge that many of the entities may have overlap spans. Say, for example, here is a sentence. This paper proposed a method for temporal sampling of capillary waves. And we need to extract that capillary waves is a material and temporal sampling of capillary waves is a task. However, this type of task is hard to be solved by the traditional BL tagging framework because the traditional BL tagging framework assumes that each of the tokens will have one individual unique label. So in order to solve that problem, we use the span enumeration strategy first introduced by Lee et al. 2017. So specifically, we enumerate all possible span candidates up to a maximum length. And for each of the span candidates, we learn a span level representation and feed that to a feed-forward classifier. And for each of the span candidates, we assign them a label. Say, for example, here, for the capillary waves, we assign them a material label, and temporal sampling of capillary waves is predicted as task. And then we assign non-type to all of the other span candidates.
Hey, how you doing?
Another challenge of information extraction is that it usually requires global context. So here is an example. Tom's car broke down as he arrived at Starbucks to meet his friend Mike. "This thing's useless," Tom exclaimed as it gave off smoke. So it's impossible for us to know the entity type for this thing and it unless we know that they are actually referred with Tom's car in the previous sentence. This type of long context is usually hard to be captured by the traditional LSTM architecture. And another example why this type of global context is important is that, say, for example, if we know that Tom is physically located in Starbucks and Tom and Mike are personally associated with each other, it's easier for us to infer that Mike is also located in Starbucks. So the solution to this type of problem to capture global context is that we propose a dynamic span graph. So this is the model that we proposed. We name it as DyGIE model, which stands for information extraction through dynamic span graphs. So here is the overall architecture. We first feed a sequence of sentences as input to a shared bidirectional LSTM layer, which can capture local context. And then we enumerate all possible spans, and for each of the span candidate, we learn a span representation. And we feed all of the span representation to a graph propagation layer, which is, so this is our main contribution. So the intuition of proposing that layer is that each of the span can be regarded as a node in the graph, and we can directly link the span by using some softly predicted links, such as relation and coreference. The motivation is that, say for example, if we have two spans in the document, one of them is at the beginning of the document and the other is at the end. It's usually very hard for us to propagate information through like traditional LSTM, but we can directly link them using this type of graph links. And then we can iteratively update the information according to this automatically constructed graph structure, and we can use the updated representation to make the final prediction of relation, entity, and coreference. So specifically, there are 3 steps to do graph propagation. Say the target span we want to update is GI, the representation. And we need to first predict the edge score between GI and its neighboring node GJ. And that edge score can be obtained from either relation confidence or coreference confidence, which I will describe later. And then we need to aggregate the information from all of the incoming edges that connects the target span with all of the other span candidates in the beam. So specifically, we propose this dot product that does the multiplication between edge score and the neighboring node representation. And then we sum over that information from all of the edges. And finally, we need to determine how much information we want to keep from the previous iteration and how much information we want to take from this new type of graph structure UI. And then we introduce this gating function f, which takes GI and UI as input. And we use a sigma function to get the weight, a weight vector f that is used so f is used to do a weighted sum between UI and GI, and then we can get an updated representation GI for the next iteration t plus 1. And we repeat the same process for all of the other nodes in the beam. So here is the overall architecture of our DyGIE model. So after we do the span enumeration, we introduce this coreference graph. So basically, we link each of the span candidates using this softly predicted coreference confidence. So the intuition is that, say for example, if we have a pronoun 8, and itself is not very informative. But if we know that what of its antecedent car is a very strong indicator for it to be like a vehicle type, then we can directly incorporate that information through this type of coreference link. And then we iteratively update this by representation for n times so that the information can be propagated all of the graph. And then we use the final updated representation to make the final prediction of coreference. So here, like in our work, we do not directly try to evaluate the coreference performance. It's merely as an auxiliary task. And then we feed the updated representation to a relation propagation layer, where similarly we construct the graph by using relation confidence. And then we propagate information according to this type of graph structure and use that to make the final prediction of entities and relations. So for the coreference propagation, the edge score is a scalar, which indicates the coreference confidence that measures how likely the two spans are co-referred to each other. And the way of calculating that score is similar to Leah Lautman's 18. For the relation propagation, we first need to predict the relation scores, and this relation score is kind of different from the coreference score, which is a scalar, but relation score is a vector because there could be many relation types, and each of the relation type will have a confidence. So it can be regarded as like a special type of graph structure where there could be multiple edges that connects the two nodes in a graph. So specifically, we use a feed-forward neural network that takes GI and GJ as input, and then we can get this type of a vector of relation confidences. And then this could lead to a problem because all of the relation scores are automatically predicted, and it could be like noisy. And also like the graph itself is very densely connected. So we need to introduce some filter function to reduce the noise. So we tried many different nonlinear functions. In the end, we find that the regular function works the best, which basically we map that relation vector to a sparse vector that to set the negative relation score to 0. So it can be regarded as we just prune out the unconfident edges that have negative scores. And then we multiply this relation score to a relation projection matrix, which basically project it to the space of the span representation. And then we'll be able to do the same process as I have already described in the graph propagation part. So DyGIE is very powerful because we got state-of-the-art on 5 different data sets across 4 different domains. To summarize why we are different, so first of all, we do not need predefined graph. So the graph is completely dynamic. So I know there's another paper called Graph IE, maybe the author is here. Our work is a little bit different from that because we do not need a predefined graph. So everything is automatically unsolved. And also we do not do the traditional sequential tagging because we introduced this span-based approach to handle overlapping spans. And also we are good at capturing global context. So we test on two different scenarios. One is on joint entity and relation extraction, and the other is on overlap span detection. So for the entity and relation extraction, we test on 4 different datasets. One is on the SciERC dataset, first introduced by our work last year, and it has like 500 annotated paper abstracts. And then we test on A4 and 5, which have annotation on use domain. And then we test on the web lab protocol corpus. For the overlap entity detection, we aim at testing our performance on detecting overlap spans. So the dataset has significantly higher proportion of overlap spans. So here we also test on A4 and 5, but we follow a different setup of literature. And then we test on GIE dataset, which has a few thousand abstracts from biomedical literature. So here is the comparison between the state-of-the-art with our DyGIE model. So we can see that after introducing DyGIE model, we could significantly outperform the previous state-of-the-art. So many of the previous state-of-the-art actually has ABL or something like included already. So we are still outperform many of them, all of them actually. And then here is the result on the overlap entity extraction. So after introducing DyGIE model, we could significantly outperform the previous state-of-the-art by around like 8 FN score improvement on A4 and 5, and also on GIE as well. And here are some ablations. So we ablate by removing the coreference layer and removing the relation propagation layer on top of the DyGIE model. And also we compare with the base model that does not have any sort of propagation process. So we can see that by removing this, by adding this coreference propagation layer, we're able to significantly improve the NER result by around 1 FN score improvement. And by introducing this relation propagation layer, we could improve the performance by around 3 FN score improvement. And then we further do some other analysis on whether our model is able to capture global context or not. So this is based on one of the observations on the AC dataset. So one of the challenges is that it's very hard to disambiguate the pronouns. Say, for example, given the sentence 8 gave off smoke, like only look at the second sentence, it's hard to know whether it's a vehicle or house or whatever. But like if we know that it's preferred with Hunt's car in the previous sentence, then it's easier for us to assign it as a vehicle type. So we do the ablations by reporting the NER FN score on both all entities in the dataset and also pronouns only. So we can see that by adding this coreference propagation layer, we could get around 5 FN score improvement on pronouns only. So this means that coreference propagation is able to help us disambiguate pronouns, which further prove our hypothesis that our model is good at capturing global context. And also, we test the performance on the relation propagation layer. So the way we're doing it is that we report the relation extraction performance with respect to by varying different number of entities in the sentence. So as we can see that as the number of entities in the sentence increases, the performance decreases quite a bit. So this is not surprising because like if there are more entities in a sentence, usually it means that the sentence is more complex and there could be more like structure in the sentence. So, but as we can see that if we introduce this relation propagation layer, which as indicated in this blue curve, we're able to significantly outperform the previous alleviate that type of problem. So this could show that relation propagation is more important for complex sentences. So in summary, we propose DyGIE model, which is a general information extraction model that uses a dynamic span graph framework to propagate global context information. And DyGIE is able to extract overlap entities through span enumeration. And DyGIE significantly outperformed the state-of-the-art across 5 different datasets and 4 different domains. So our code and everything is publicly available, so please refer to our repository. Thanks.
This is a very interesting work. So it seems like all the performance improvement really is about like how you construct a good graph, right? And then you can get this large improvement. So in your ablation study, I didn't see too much ablation study about what's the effect of the graphs and what kind of choice. For example, you have some kind of ad hoc scheme, right, to choose when to remove some of the edge that maybe create some noise, right? Because originally the graph is a very dense graph.
Yes, yes.
Yeah.
Actually, it's not ad hoc. We tried many different ways of reducing noise. Like, so basically, like we're trying to figure out unconfident edges. So, like for example, in the relation graph, we introduced this radial function that basically just map like just reduce the number of edges that connects between two nodes. Because like in the end, like maybe only one of the relation type will hold between each of the span pairs. So like we just use this radial function that basically set all of the negative scores to 0. That means that if the relation confidence like is lower, then we just prove them out. So it's not really ad hoc. We just add the simple non-linear function to figure out that.
So there's no other hyperparameters that you have to tune for construct this dynamic graph?
So we are actually following Kenton Lee's work on Coreference. So he introduced like a beam pruning strategy, and so I didn't talk too much about that in our work, but it's actually kind of important on how much span candidates we want to keep in the beam, because like usually if you include all the span candidates, it results in like lots of candidates, and it's hard to construct the graph. So like we basically restrict the beam size so that we know how much information we want to keep.
Okay, thank you.
Yeah.
Any intuition about why the junior is building gets as much gain as other SDs?
So that's a very good question. I think one of the things is that Genia is on the medical domain, and actually we tried. I think there's a side animal something. so like if we like use like animal like version trained on scientific domain, and it improves them. And also like the Genia data set itself has a lot more data, around like 2,000 data or something. So yeah.
Thank you.